Okay, so continuing to that, so we have a hyperspectral remote sensing as an extension, okay, to multispectral remote sensing. We are going to discuss further later on why it is considered as an extension. Okay, but more or less, I can say that in general, it is still an optical system in terms of the operational mechanism. It is still the same like multispectral, in which it is depending on the energy reflected from the sun, and the sensors will measure the reflected energy from the sun. Okay, so, and also the operating spectrum. Okay, the electromagnetic spectrum in which the multispectral and hyperspectral systems are operating are pretty much the same, okay, which is between 0.4 to 2.5 microns mostly. Okay, so it covers the visible range, the near infrared, as well as the shortwave infrared. Okay, but the main difference between multispectral and hyperspectral system are actually located at the spectral resolutions, as well as the number of the spectral bands in the system. So we're going to look into that a little bit later. Okay. Okay, so we are going to discuss about some basic principles of hyperspectral remote sensing. I'm going to explain about some common ways of acquiring the data. Okay, what are the data acquisition techniques that we can use? What are the data analysis flow? Okay, how we can analyze the data? What are the options that we have? And what are the common applications of hyperspectral remote sensing? What are the issues? Okay, and so on. Okay, so just to recall again about the concept of data science. Okay, I always have to, or I like to remind all of you that we are in the domain of data science, and in remote sensing is part of data science, because remote sensing is all about delivering data. Okay, it's acquiring, delivering, as well as processing the data for applications, okay, that might be of interest to us. Okay, so in data science, you need to have some skills. Okay, for example, you need to know a little bit about programming. Okay, a little bit about machine learning. You need to have some understanding about the statistical analysis, as well as what is the business issues that you're trying to tackle, okay, by the use of the data. Okay. Okay, so once you have defined, okay, your problems or the business issue that you're trying to solve. Okay, let's say, for example, I'm using remote sensing to increase the yield of my oil palm plantation. For instance, if I am a plantation owner, okay, I want to know how can I detect, okay, problematic oil palms in my plantations. Okay, so once I define that problem, I will go to, I will think about how I'm going to get the data. So whether I'm going to use UAV, whether I'm going to use satellites or whatsoever, okay, I have to define the way of acquiring the data, as well as what sensor will be the best, okay, to deliver the information that I need. Okay, so maybe in this case here, let's say I decide that if I want to detect oil palm health, the best probably is hyperspectral remote sensing, and I'm going to use UAV. All right, so I need to either buy a system, okay, if I have lots of money, okay, to buy a system, or I can also go for service provision, okay, by vendors and so on. Okay, and then once I got the data, I will decide whether I will just process the data myself. If I have an analysis, or if I have analysts, okay, for my plantation, I can just take the raw data and do the processing myself, or I can source out the processing to the service provider. Okay, in either way, the same workflow will be carried out. Okay, in which the first step will be data pre-processing or cleaning up the data, right? It is also known as data wrangling. Okay, where you clean up your data. Okay, you have to make sure that your data is ready, okay, to be processed further, because as I mentioned last week, your raw data will be subjected to lots of disturbances, okay, during data acquisition. Okay, what kind of disturbance or errors that might occur during data acquisition, you think? If, let's say, for example, if we have if you have a UAV, yeah, and then we fly our hyperspectral sensor over a particular area, what do you think will be the distortions that might affect your raw data? Okay, let's say, for example, firstly, I want to clean my data. Of course, every time you get your raw data is always noisy and affected by a lot of factors. Okay, you need to clean it. So data cleaning or data wrangling is a very crucial part, okay, to ensure that your data is ready to be processed. Because in data science, the principle of data science, that's rubbish in, rubbish out. Okay, so means that if your data is rubbish, your outcome also will be rubbish. Okay, so you have to make sure that your data is clean, right, and ready. Okay, so if you fly a UAV with sensors on board, okay, in your opinion, okay, what can be the factors that can affect the quality of my data?
The cloud, maybe, doctor.
Okay, so what will the cloud do to your data?
It will make our image unclear. We can see the image uh, in a better quality.
Okay, maybe one thing is cloud. Maybe cloud can, I mean, the presence of cloud or haze, okay, can affect the clarity of the data. Yeah. Okay, so you have clouds, probably, so maybe some haze. Okay, so you need to sort of how you're going to correct for the errors related to the haze presence in the data. What else can affect your data, you think? How about neural iron? Okay, what is your, I mean, what do you think will be some of the errors that may occur during data acquisition? So Nuruain, you have any ideas?
I have no idea.
No idea? Maybe you can guess, you can imagine. If you fly a UAV, right? What can happen to the UAV? Any of you have tried to fly a drone? Maybe a toy drone?
Yes, doctor.
And Muhammad, siapa tadi?
Saya, doctor.
Ya, apa nama, what's your name? Saya tak nampak your full name, sorry.
Muhammad bin Rashid, doctor.
Muhammad, yeah, okay. So you have maybe you have played around with some toy drones before, right?
Yes.
Okay, so for what purpose? Is it for photography or what?
Yeah, photography tu.
Okay,
Videography.
so that is quite similar to what we are doing now with remote sensing. So what kind of problems you got when when you try to acquire the images from UAV?
First, when I fly the drone, maybe the air pressure too high, so the drone will fly away.
Mm-hmm. Okay, good. Okay,
Another second one, technical problem which is battery. So really ineffective the battery.
okay,
The third one is maybe from eagle. I was chased, the drone was chased by the animal.
okay. Oh, okay, good. Yeah, okay. I mean, that is a very good experience for you, Muhammad. And what you have mentioned just now uh, are something that are faced by the drone operators as well in the industry. Okay, even though you're using it for just for fun or for hobby, but for those who are doing it for real serious business endeavor, right? They also face the same thing as you mentioned. All right, so that is very good. Okay, if you, I mean, you can also take some. I mean, you can also take drone pilot license as well. Anybody can take it. Okay, if you really like this particular hobby, you can be a drone pilot. Okay, and we don't have enough drone pilot in Malaysia at the moment. Okay, and there are a lot of things that require professional pilots. Okay, to operate drones. Okay, so that also can be something quite interesting. Okay, because a lot of applications nowadays will use drone. In fact, going to the future, there will be a lot more drones will be used for a lot of operations. Okay, in oil and gas. Okay, in maintenance, even in construction and so on. Drones will be the usage of drone will increase. Okay, tremendously. Okay, as what mentioned by Muhammad, that was very relevant to what is going on in the industry at the moment. So when you fly a drone will be subjected to a lot of factors, for example, wind and turbulence, okay, and also air pressure and things like that. It will cause your image to be distorted. Yeah, your image will be distorted, especially when you are working with hyperspectral sensors on board. Hyperspectral sensors is much more sensitive compared to normal what you call it aerial camera. Okay, so all this distortion will be much more apparent in the image. So errors coming from the platforms and coming from the atmosphere, okay, will affect the image that you acquired initially, okay, at the raw level. Okay, so that's the thing. So that's why you have to do data wrangling or data preprocessing, and then once you have corrected your data, okay, then next will be the data analysis and modeling part. Okay, so this is where um, you will pass your data to maybe an analyst or a data scientist, okay, and he or she will be doing all this information extraction, okay, from the data, okay, in order to analyze, in order to generate or create models, okay, for classification, for regression, and also for predictions, okay. And once these models are finalized and considered as acceptable, then the output in terms of the maps and models will be deployed or delivered, okay, to the clients, or they will make it available as a web applications or things like that. Okay, so this is the process. Okay, so similarly, this is also what we do with hyperspectral data. It doesn't matter. I mean, any types of data we're talking about in any domains. Okay, it's not necessarily in geospatial domain, but in other domains as well. Whether you're talking about finance, you're talking about insurance, you're talking about what else? Maintenance, retail, or whatsoever. Okay, because data science covers everything. Okay, data science covers everything, and your data will be in many types and forms. Okay, in geospatial data, when we're talking about geospatial data, why the data is classified as a geospatial, is because the data got location information. If you just have an image, without any location information, okay, it only can be considered as a partial geospatial data, because you don't include GPS information, okay, with the data that can provide information about the position and also the location, the latitude, longitude, as well as the X, Y, and Z. Okay, this is not included. So if that are not available in your data, then that is not a complete geospatial data. Okay, but a geospatial data normally, okay, will be delivered, okay, with X, Y, and Z component. Okay, the X, Y means the spatial component. Okay, the X and Y are the spatial components. Okay, and the Z are basically the location component. All right. So these are the characteristics, okay, of a geospatial data. And geospatial data are commonly applied in many applications. In civil, for example, if you think about it, there are a lot of applications of geospatial data in civil. And in terms of data acquisition, okay, in terms of the platforms, okay, in general, there are three types of platforms that you can use to acquire remote sensing data. Okay, the first one is called a ground platform, okay, which is located very close to the object of interest. Okay, so ground data can also be acquired from lab measurements, okay, from field measurements, okay, and after that you will have airborne data. So airborne can be from piloted aircrafts or from UAV, all right? And then after that, you go to the spaceborne level or the satellite level, okay? So in terms of the sensors, okay, there can be multispectral, can be hyperspectral, can be LiDAR, okay, as well as radar. Okay, these are the common types of platforms and sensors that we use in remote sensing. Hyperspectral data can be acquired from all these platforms, okay, ground, airborne, or spaceborne. I'll just skip this one. Okay, this is the electromagnetic spectrum that I have mentioned, and maybe also last week we have already visited this. So the electromagnetic spectrum that always of interest to optical remote sensing is from about 0.4 to 2.5 microns mostly. Okay, and beyond that, they belong to the active systems like radar, microwave, and so on. Okay, so we focus from 0.4 to 2.5 microns. Okay, and in hyperspectral remote sensing is the same, right? So you can see that multispectral and hyperspectral remote sensing, the main advantage of hyperspectral and multispectral remote sensing in comparison to the normal RGB camera. So Muhammad, just now you mentioned about you have flown UAV with cameras. I believe that you use the normal aerial photography camera, right?
Yes, sir.
Okay, so that is only covering a very short range from 0.4 to about 0.7 microns. Okay, so it's not actually enough to cover a lot of things beyond our vision. Okay, we want to see things beyond our visions, because in the spectrum beyond visible, there are a lot more information that probably can be known to us. Okay, so we use sensors to do that. Okay, so as I mentioned, multispectral remote sensing is an extension of hyperspectral remote sensing is an extension to multispectral remote sensing. You can see the you can see the significant differences between these technologies. Okay, multispectral remote sensing has been around since the 70s up to now. Okay, so but of course they have improved in terms of the spectral resolution, in terms of the spectral sensitivity and things like that. But in terms of the number of bands, okay, they are still quite limited, right? Landsat, for example, Sentinel, for example, they will not go beyond 20 bands. Okay, so that is the main limitation. We can say that is the first things that you see in terms of the difference between multispectral and hyperspectral. If I give you a data with hundreds of bands or thousands of bands beyond 20 bands, for example, automatically you can classify that as hyperspectral. Okay, because hyperspectral, okay, the first thing that will make it different from multispectral is the number of bands. That's the first thing that we can notice directly. Okay, so when you look at the data like the bottom one, okay, for example, coming from hyperspectral system, okay, you can see that the data now is very, very detailed. Okay, this is a spectrum. Okay, you know what is a spectrum? A spectrum is basically we call it the information about the reflectance, okay, over, when it is plotted over a range of electromagnetic spectrum. Okay, for example, you have a spectrum from 0.4 to 2.5 microns in our case now, for instance, or it can also be presented as the band number. Okay, so when you plot the value of the reflectance for every band, okay, per pixel, okay, you will get plots like this. Okay, so multispectral, when you have multispectral system, the plot or the spectrum is very, very generalized because you have only very limited number of bands. Okay, on the other hand, if you have a hyperspectral data with hundreds of bands, like in this case here, you can see the details. Okay, when you plot the data, it's like similar to what you did with your topographic data. Remember, when you have topographic data, okay, when you have a topographic data, when we talk about the resolution of the digital elevation model, okay, if you have a 5-meter resolution versus a 10-meter resolution, you can see that a 5-meter resolution will be better description of the topography compared to the 10-meter resolution. Okay, so similar here. Okay, when you have number of bands bigger or more than maybe 10 or 20, so you can start to plot the details. Okay, and when you have the details, you can differentiate the different levels or the different types of land cover or land use in a much more effective way. Okay, so let's say, for example, you have oil palm. Okay, if you plot four levels of oil palm, okay, let's say, for example, you have level 1, which is healthy, level 2, which is slightly unhealthy, and number 3 is unhealthy, but they are still green, when you use your naked eyes, okay, to look at all these oil palm trees, to us, they are all still a green palm tree. Okay, but when you use a multispectral sensor, when you plot the spectrum, you might still not see the difference between them because the pattern might still be the same because you don't see the details much. Okay, but when you use hyperspectral data, when you plot the reflectance of the 3 levels of oil palms, you will start to see the differences in terms of their reflectance. And this is telling you the differences in their health levels. Okay, this is something that we cannot see from our naked eyes, something that we cannot see from our multispectral systems, but can be seen, okay, from hyperspectral systems. Okay, and this is also one of the reasons why hyperspectral system is being employed. Okay, it's simply because it will tell you more than what you can see from multispectral systems. So this may be useful for the plantation industry to detect problematic trees okay, before they become serious, so that they can do, we call it quick treatment on problematic trees, so that these trees can have the chance to recover. Okay, so we are going to look at how we use, how we analyze this sort of differences electron in our practical sessions. Okay, because Mr. Yu Hao got some, what call it, the samples. If I'm not mistaken, it is soya bean samples, right, Yu Hao? We have some soya bean samples with different levels of disease infection.
Yes.
Yeah, so we are going to play with that today, hopefully, by using NIME software. Okay. Okay, so this one I have already mentioned to you what are the characteristics and advantages of the systems, and how, for example, we plot our data if we have the imageries. Okay, so normally you will be presented with, or you can acquire images, okay, from the UAV or satellites. Okay, and for every single pixel, okay, if you got a chance to play with QGIS later on in your own time, okay, you can plot the spectrum for every single pixel. Okay, if you go to the pixel of water, for example, you will get the plot representing water, okay, a plot representing soil and vegetation and so on. And these are basically the basis of image interpretation, and also the basis for classification. Okay. Okay, the same thing. Okay, as I mentioned, this is the differences. This is the difference between multispectral, hyperspectral, and ultraspectral. Okay, multispectral, we have only few bands, very broad. Okay, you cannot see much in terms of the differences between very similar types of land cover. However, if you go to hyperspectral, normally you go for beyond 10, 20, you have 100. And ultraspectral is a kind of data that you can obtain from very close range field and also lab spectrometers. Okay, if you have a lab or if you have a field spectrometers, you can get data with up to thousands of bands. And this is even this is even much more detail, lot of more detail you can capture. And normally this kind of data is being used as the reference, okay, or as the benchmark. Okay, they will use ultra spectral data acquired in the lab or in the field, okay, as a reference to identify what are the pixels, okay, that are being seen by airborne or by spaceborne systems. Okay. Okay, these are just some visualizations of the differences between panchro, multispectral, and hyperspectral. So panchromatic is a single band. Okay, it's a single band. And normally, when you display your hyperspectral images, you can see that your data, let's say, for example, you have 100 bands. And these 100 bands, if you look at them individually, okay, the individual band will be presented as a grayscale image or as a panchromatic image. Okay, it is just a black and white image. On the other hand, if you use, we call it multispectral, okay, you can combine several bands together, okay, to help you in the visualization. But when you use hyperspectral, you have much more options to combine the bands. Okay, when you have more when you have more combinations, or when you have more options to combine the bands, your ability to see things that are more subtle to the naked eyes will be higher, right? So you might detect certain things that are hidden from normal cameras. Okay, maybe a presence of pollution, presence of materials and things like that, okay, can be seen from hyperspectral images. So for example, hyperspectral images, they have used hyperspectral images to detect landmines in Cambodia or Vietnam, for example. Okay, they want to clear we call it the anything. I mean, you know that Vietnam, Cambodia, they were subjected to serious pollutions due to landmines after civil war and so on, right? So nowadays, they need to clear the land, okay, for further development, for plantations, maybe for residential development and so on. It is very dangerous, okay, if somebody step on the landmines, okay, so, or booby trap or whatever. So they use hyperspectral in order to detect, okay, the landmines, okay, for the purpose of clearance and so on. Okay, this is a difference, just to show you an example of a difference between a green leaf spectrum. Okay, if you use a Landsat, for example, the plot will be very coarse, okay, very generalized. But when you use hyperspectral, you can see the difference. Okay, so you can see the details, and the details in the hyperspectral system might indicate, for example, how much chlorophyll is there in that particular leaf, how much water is there in that particular leaf, nitrogen, okay, and how healthy it is, okay, in comparison to certain benchmarks. So that's why hyperspectral data is being used a lot in plantation, for instance. Okay, so in general, this is the differences, okay, between multispectral and hyperspectral, okay, in terms of the number of bands, in terms of the width of the spectrum, as well as the image size. Okay, so when you have multispectral data, the volume or the size of the image will not be as large as the hyperspectral systems, because when you have more data, you have more information, the volume of the data also will increase in terms of the size. Okay. Okay, this is just an example of data coming from Landsat and also from Hyperion. Okay. As I mentioned last week, Landsat is one of the most successful multispectral systems that is still being operational. Okay, and it is still up there. We have Landsat 8 as well as Landsat 9. Okay, and Hyperion is the first satellite-based hyperspectral system being launched into orbit in 2000. It's already retired now, but there are also other systems that are operating, but we don't have as much access, okay, to the data like Hyperion before. Okay, so you can see here from the specification there are some differences and similarities. In terms of the spectral range, they are very similar. Okay, but in terms of the number of bands and also the spectral resolution, they are different. Okay. Okay, this is a standard workflow that I have already mentioned just now in terms of data acquisition, processing, and delivery of the products. Okay, in terms of the techniques, for data acquisition, I would like to mention to you about the different techniques that we use for data acquisition. Okay, field measurements as well as lab measurements can be used to acquire spectroscopic data at the finest level. Okay, and then after that, for operational purpose, for mapping over large areas, for detection of minerals, okay, and so on, we use airborne as well as spaceborne hyperspectral sensors. Okay, this is an example of how you operate the field spectrometer in the field. Okay, so you will carry the instrument in the field and you identify the targets, okay, and you acquire the spectral data, okay, close to the target of interest, but still not in contact, okay, but it is quite close to the target of interest. Okay, so normally you will use this, okay, in order to get reference data or to verify what are the things on the ground. Okay, so normally we used it for verification and also development of spectral libraries. Okay, you can also take your samples back to the lab. Okay, if you think that the samples, if you don't have time, okay, to measure the data in the field, because maybe there are problems with the illuminations or maybe problems with weather, okay, you can take your samples back to the lab. Okay, but you have to be careful when you take your samples back to the lab, especially when you are dealing with vegetation samples, because you need to cut the vegetation. Maybe you need to cut the leaf and so on. And every single moment after you cut the leaf, there will be degradation, okay, to the life of the plant, for example, okay, because you cut and now the supply of probably water and nutrient will be degraded over time. Okay, but if you have samples like geological samples, yeah, maybe rocks, rock samples, or maybe mineral samples and so on that will not degrade as fast as vegetation, you can take them to the lab, okay, and do measurements in a much more controlled environment. Okay, outside, if you do the measurement outside, there will be changes due to illumination as well as excess. Okay, so maybe you can take the samples back to the lab, okay, and do the measurements in the lab. Okay, for example, yeah, we can see the in the room of Dr. Zainuddin, for example. Yeah, you have taken classes with Dr. Zainuddin, right? Right.
Yes.
Okay, and you have been to his office. You can see a lot of rocks over there in his office, a lot of samples of rocks. Yeah. So we can take the samples and do the measurements in the lab or in the office. Okay, by using this sort of setup where you control the illuminations and so on. All right, and you can do the measurements in the lab. Okay, so once you have taken the measurements in the lab or in the field, okay, you will have data like this. For example, this is an example of data of soil. Okay, this is an example of data of soil of different grades. Okay, for instance. Okay, and the different grades might correspond to different levels of minerals in the soil. Okay, or to different levels of maybe strength of the soil or things like that. Okay, so maybe you are studying the possibility of using remote sensing to predict soil strength, okay, from spectral reflectance, so that you don't have to every time do destructive testing and so on, okay, or maybe you wonder whether remote sensing can be used to replace time-consuming and expensive we call it experimentations that need to be done in order to determine certain properties of materials. Okay, so you might take some measurements in the field or in the lab like this one, and you know that they belong to certain grades. Okay, you have some, you know, what we call it, control, okay, over these samples. So you might see the patterns like this of the different soil grades, okay, but maybe this is only a visual. I mean, it can help you at the first phase to determine whether there are any visual differences between the grades and so on from the reflectance data. But what you need to do next is you really have to go and process this data through some mathematical or statistical analysis to know at which wavelength, for example, is the most important information is residing. Okay, for instance, okay, because you have over here from 0.4 microns or from 400 nanometers to 2400 nanometers, there are so much information contains, you have lots of information that is being hidden inside this particular range. All right. So you want to know you have several research questions. For example, what are the most important wavelength points, okay, to differentiate between the different soil grades, okay, and what this will correspond, okay, to the different level of carbons and so on. Okay, because what is important is that later on, from this information, you can, actually this information is the fundamental information. Normally the engineers, for example, like electronic engineers or we call it electronics or electrical engineers that are responsible for designing, okay, they are responsible for the design of new sensors, okay. So they are interested to know whether they can design sensors that are cheaper, okay, and can operate within less number of bands. Okay, in this particular case here, you have maybe thousands of bands, and to fly these bands over using an aircraft or using a UAV will not be feasible. Okay, so you need to design much lighter and smaller sensors. If you want to design lighter and smaller sensors, okay, you need to reduce the number of bands. Okay, and by analyzing this sort of information, you can determine what are the most important bands. Maybe out of this 1,000, there are only 10, the most significant bands. So this information is important for the engineers to design 10 bands sensor that can be used specifically for mineral application, for instance. Okay, so in that sense, they can just produce or manufacture this 10 bands sensor, which is lighter and cheaper, okay, that can be operating by using a UAV, okay. Later on, they can use it to fly over a particular mining area and detect certain minerals and things like that in much more cost-effective way, right? So that's the thing, okay. Another thing, yeah, I mean, you want to know, for example, things like disease, okay, even human disease or skin disease, for example. Hyperspectral sensors has been used a lot, okay, for analyzing a skin disease, okay, because that's the easiest part of the human body that can be assessed, okay, by using imaging systems, okay. So they use a hyperspectral sensor to detect, for example, the presence of the potential early presence of tumor on the skin, okay. They can analyze the moles and things like that, okay. And hyperspectral has been a lot, okay. They have been, I mean, hyperspectral sensors have been used a lot in precision farming, okay, in order to detect plant disease, okay, by analyzing the spectral information at certain wavelengths, okay, to see the differences that can be an indicator of a disease in the plant, okay. All right, this is also what you're going to do in the practical sessions in a bit, okay, later on. Okay, this is how we conduct airborne survey. This is similar to how we conduct normal aerial photographic data acquisition, the same principles, okay, where when you fly by using either UAV or aircraft, you have to make sure that there is an overlay between one strip to another strip to ensure that, okay, there will be no gaps between data when you do data mosaicing, all right? So this is a similar principles. In terms of the imaging spectrometers, there are a lot of imaging spectrometers out there, okay, either commercial or civilians, okay, but most of the imaging spectrometers are commercial. Most of the hyperspectral sensors that are being operational, they are commercial because these systems are very expensive, and yeah, I mean, they normally being used for certain business applications like mining and so on, okay. So they are mostly commercial. Hyperion is not commercial. You can access Hyperion data before, but it is no longer operational in terms of acquiring new data. Hyperion is already retired, but you can access the what you call it, the archives of the data from the NASA website. Okay. Okay, that's Hyperion. Okay, these are the current and also coming okay, sensors. Hyperion is already there. China also, they have their own hyperspectral system, but of course it's not accessible. Recently, Italy launched spaceborne hyperspectral system called Prisma, okay? But we don't know yet whether the data is accessible or not to public. And Germany is planning to launch NMAP, okay, in 2022 actually, but depends whether this year or next year. All right. So these are all the coming systems that probably we can have access to their data. Japan already, they launched the Hisui hyperspectral system. It's already operational. We can request the data from Japan space systems. Okay, but we have to check whether they cover Malaysia or not. These are the, what we call it, the others. All right, so after this, this particular diagram is actually dealing with the image processing part. Okay, when you have image data, okay, this is the flow of the methodology that normally we will carry out in order to process our imagery data. Okay, I'm not going to dwell on that today because we will do that next week. Today we are going to focus on field spectroscopy first. Okay, we will do the image analysis later on, hopefully next week. Okay, and all the procedures and things like that. Okay. Okay, so before we stop for the practical, okay, I'll just go through. I'm not going to discuss about this procedure yet today because this is a very specialized area that you need to understand. Okay, when you have the image. Okay, because at the moment you are yet to play around with the image, even with the Landsat or Sentinel. So I think I will skip this for a while, but I'm just going to give you so that you have the mental framework that this is the thing that you can that you will come across pretty soon later on in terms of the processing, okay, of our imageries. Okay, we have all these steps that we need to carry out. In terms of the applications, of course, there are so many things if you want to talk about applications. Okay, even I give you the assignment recently on Putra Blast. Okay, I asked you to go around and check for the applications. So I believe that it is a never-ending story if you want to talk about application because the applications are so many. Okay, but we can see that the most applications, the majority of the applications of hyperspectral can be found in agriculture, especially in precision agriculture, as well as in food assessment. Okay, food assessment at the production level. Even now in Malaysia, we are trying to develop a system based on hyperspectral systems in order to detect halal or non-halal kind of meat and so on. Okay, so this is something that UPM is working on. Okay, we are working on a system now with the food science faculty. Okay, we are trying to develop a system based on hyperspectral to detect the quality of meat. Okay, and to determine whether it is halal or non-halal. Okay, we can also use hyperspectral probably by analyzing the spectral component as well as the image. Okay, in terms of for forestry, they have used a lot hyperspectral data in order to determine the species in the forest. Okay, so using multispectral, it is very difficult. But if you have hyperspectral data, it is possible for you to see the differences in terms of the species at the canopy level or at the tree level. So when you know the species, you can do precise logging. All right. Okay, you can pinpoint the trees that are of interest, and you can go and log that particular trees. Okay, without having to interrupt much of the neighboring trees. Okay, without having to do much of the damage. Okay, so in terms of the environment, of course, a lot. Okay, into utilities and transportation, also we can use that to assess the health of our infrastructure, okay, the materials, the deterioration. Of course, for military, this has been a lot. I mean, this has been used a lot. In fact, this is why hyperspectral was invented in the first place, for military applications, to detect, we call it fake materials on the ground, or to identify targets. Okay. Okay, for health applications, we can use that for cancer detections, for food quality assessment, water quality, and so on. There are a lot of things. In terms of issues, these are all research level issues, okay? Because at the moment, hyperspectral, despite being very powerful, okay, still the usage is limited, because the main thing is because of the cost, okay? Even though we have got hyperspectral size, UAV size hyperspectral sensors that can be carried on board of UAV, which reduce a lot of burden before. Before the use of UAV to acquire hyperspectral sensors, we have to use a piloted aircraft. So when you use piloted aircraft, you need to check the availability of the pilots, you need to pay the pilots, you have to rent the aircraft and so on. The operational cost is very, very high. Okay, but when you have the UAV and you have the micro hyperspectral sensors, okay, you reduce the requirement to have the pilots. Okay, you can now fly that on UAV, and you can fly it at any time under the cloud. Okay, and this can reduce the cost to a certain level. But still, the cost is still prohibitive, because the system is not widely available. So when we have only limited number of vendors, there tend to be some monopoly in the market, and they can play around with the price, okay, with the less competition. So there is also another problem that we are facing at the moment in the industry, okay. So we hope that there will be new sensors coming in with much cheaper, okay, with better UAVs, as well as we need to have the pilots, okay, to operate the sensors, to operate the UAV, okay. And battery also is another issue. Yeah, battery is a crucial issue, because when you fly hyperspectral sensors on UAV, based on our experience, UAV is also a limiting factor. Sorry, battery is a limiting factor, right? So it is we need to have a much more robust and long-lasting battery in order to operate the UAV over a long period of time. Okay, because they need to fly many, they have to fly and acquire many strips, okay, to get the mosaic. Okay, yeah, so before we go to the practical side, okay, you have any questions so far? You have any questions so far?
No, no.
I think okay, Doctor.
No, Doctor.
Okay, just to give you a little quiz. Okay, you still remember what is the name of the first hyperspectral sensor in orbit? What's the name of the first hyperspectral sensor in orbit? I just want to test whether you're alert. How about Nur Shaza? You still remember? Nur Shaza Azira. What's the name of the first hyperspectral sensor in orbit? Are you around, Nur Shaza?
Sorry, Doctor. My internet problem.
Okay. How about Nur Alia? What's the name of the sensor? I cannot hear you.
Landsat satellite.
The name of the first hyperspectral sensor in space.
I think Landsat 9.
No, it's not Landsat. Landsat is a multispectral system, and Landsat 9 is obviously not the first. What's the name of the first hyperspectral sensor in orbit? Still remember, Alia?
No, Doctor.
How about siapa Just want to check whether you are still here. How about Lukman? Sorry, Lukman saya dah tanya kan. How about Iqbal, Muhammad Iqbal? What's the name of the first hyperspectral sensor in orbit?
Not sure.
Ada dalam slide tadi. How about alright. Siapa lagi saya nak tanya ni ya? This slide is already I have already shared with you in Putra Blast. I hope that you have downloaded. How about Amirah Afikah?
Yes, Doctor. I think UAV.
UAV is not a name of sensor. That's why I need to ask you this sort of questions because I just want to make sure that you stay alert during my lecture. Otherwise, I'll just be talking alone because that's a problem with online system. Okay. Kalau dalam lecture tu, I can see that you are there in front of me kan. So over here, I'm not sure. So that's why sometimes I have to ask you questions so that you stay alert. Alright. Okay, tak apa. Kita teruskan dengan soalan kuis ni. How about Nur Farah Izzati? What do you think? What's the name of the first hyperspectral sensor in orbit?
Yes, Doctor.
Yeah, what's the name of the first hyperspectral sensor in orbit?
I'm not sure, Doctor. I'm sorry.
Mana tak sure? You all buat apa masa saya punya lecture? Oh, ini soalan senang ni. Tak sangka pula you all tak dapat ni kalau masuk test 1 ni ramai yang tak lepas ni. Okay, so how about Haris Daniel?
Is it Sentinel?
Salah.
Hyperion, Doctor.
Who's answering that?
Me, Pei.
Okay, so good, Pepe. Tak sangka pula this question is very difficult. Okay, okay, so Hyperion is the correct answer. Okay, if you listen to my lecture carefully just now or you refer to my notes, Hyperion is the first ever hyperspectral sensor in orbit. Okay, on board a satellite. Okay, so Hyperion is a legend in hyperspectral, you know. So you have to know what is Hyperion. Okay, it's a legendary sensor, the first ever hyperspectral in orbit. Okay, so okay, good, Pepe. Okay, so before we go to the practical, okay, I just need to record your attendance once again. Okay, switch on your camera, please. Okay, before we go to a break and we'll start with the practical later. Switch on your camera so that I can be sure that you are still here. Just 1 second. Okay, 1, 2, 3. Right. Okay, thank you very much. Okay, for your cooperation. You dah sign the attendance, yeah? Okay, so before we take a break, okay, just to explain to you what's next. Okay, after this, Yuhao will be explaining to you about the practical. Oh, sorry. Just let me share. Okay. This is our plan. Okay, for the practical. Okay. Today we are going to do a spectroscopic data analysis by using NIME. Okay, NIME is a software, and we're going to analyze some data. I think vegetation data that was acquired in the field or in the lab. And next week, we can do some hyperspectral image analysis using QGIS and some. Okay. Okay, so we can take a break here. We can take a break for like 10 minutes. Okay, we'll come back at 10:25, and Yuhao will straight away explain to you about the practical. Yeah, so now we take a break for 10 minutes. We'll come back at 10:25.
Okay.
Good morning, everyone. Before we begin our practical sections today for the analysis of the spectroscopic using NIMES, I have shared the practical slide that we are undergo last week, and also the Sentinel-2 image in the Google link. So you can download from there and then refer to the slide. And at the last page of the slide, I also put some reference. So you can refer and try it later on. Since today we will move to the spectroscopic analysis using NIME. So the guide for the last week has been provided. So if you have any questions, you can WhatsApp me later on. So without further ado, I would like to share my slide for today's sections. Okay, I have shared my slide. Can you guys see my slide?
Yes.
Yes. Yes, sir.
Okay, good. So in our previous sections, I have introduced on some of the installations. One of them is NIME. So today we will be using NIME software for our spectroscopic analysis. So may I know how many of you have downloaded the NIME software? I'm sure all of you should be having that now. Have you guys already downloaded this software?
Yes. Yes.
Okay, good. Good. So let me make some introductions. I think I have shown to you NIME have a big platform and community. So it is very inconvenient, and specifically nowadays is used for the data analysis. So today we will expose and try the exercise using this NIME software. And also okay, so as you open your NIME software, this is the interface that we will be seeing. So it has, in this NIME interface, it has a few of the portions: NIME Explorer, Workflow Coach, Node Repository, Workflow Editors, Node Descriptions, and Console. So before I begin, I think I would like to share the data and also some of the materials. Just a moment. Okay, I have shared the one of the link that we can access on that, and also inside that there are the data we will be using today, and also some of the installations for the plugin we'll be using for the Seveski later on analysis. So some of the data practical material inside. So, and also the workflow of the NIME for today's session. So I have shared in the chat box and also WhatsApp. You can download. Okay, so if we open the NIME software, it will be looking like that. So I will briefly make some brief introductions. Okay. Okay, so from the left, the NIME Explorer. What is the NIME Explorer? The NIME Explorer is every times when we want when we are doing some analysis, we want to save our workflow. We call it workflow. So so when we want to save our workflow, we need to save in somewhere. So here is the place, the information, the place where we have saved each of the workflow or analysis. So this is called the NIME. This is the functions of the NIME Explorer. That means every time when we run or we do any analysis for our particular work, so what we have saved our workflow in somewhere else, it will be saved here in one of the directory user local workspace. So you can refer from here every time. That means and restore back the workflow. I mean, maybe you have saved it last week, and then today you want to check and then to restore. So you can open it and drag it. For example, I double click, so it will load the workflow. So it is quite general. It is loading. So the more things has saved inside one particular workflow, so it takes some time. So now it has been open it. So but today first we will be using this. Okay, so for the second one, workflow coach is to give the hint for every workflow we are going on. And then the third one is the node repository. So every time when we want to use some of the function inside the node, we just drag and drop. You can see here, drag and drop. So this is quite a core for the analysis. If you want to add, after the row filter, we want to, let's say, to plot a scatter plot. So we just drag and drop. So we just drag and drop. So later on it will it will suit to our purpose. So for the this one workflow editor, this is the main the main place that we will be using, and then frequently. So when we are doing each of the operations in the analysis, so we will be using this place. So that's called the workflow editor. And outline, so the outline is zoom in and zoom out. After that, node descriptions. Okay, the node descriptions is referred to, for example, it will provide, if you click on the certain, just now I click on CSV reader, what is the function of the reader? What's the function of this node or this CSV reader? So you can refer from here. So otherwise it can be store or minimize first. Okay, so the console is to see if every error that if it occur during the process, and it will be mentioned there here. But if it has successfully passed, it will also mention there. So we have basically see the general interface from the NIME analytics. So today the section will be divided into two parts. One is I will introduce and show some of the basic NIME analytic before we go into the field spectroscopy analysis. There's the second part. So the second part, we will be using the field spectroscopic analysis for classifications using some of the machine learning algorithm techniques. So later on, second part, we will be exposed to the general workflow of machine learning or AI analytics. So there's the second part. But before that, we need to learn the first part on the basic NIME. How is the NIME operate, and then and the rule of in using the NIME. So in this part one, there are 3 lessons. So the first lesson is data access. Workflow group, and also importing, accessing, and reading the data from the files. Okay, so as I roughly show just now, I drag the node from the node repository. So you can see here the node. So node is the one of the component in the workflow in the NIME. So that means in one workflow, it will have several nodes. So that means the component of the workflow. So workflow can have many functions. So depending on your purposes. So for example, CSV reader is also node, and table reader and CSV reader. So this is called node. So 1 node, 2 node, and 3 node. Later on, a few of the nodes workflow comprises or consists of a few of the nodes, but depending on our specific analysis. So it is quite straightforward. So before so let's go to the next one. So as you can see, the workflow is the consists of a few of the nodes. So it is called workflow. So later on in the second part, we will see the machine learning workflow. We will be exposed to the machine learning workflow using NIME. So it will consist of the several nodes, and then it will be making up to the one workflow as one workflow. And now we go to the importing, accessing, and reading the data. So there are many ways to import, to access, and also to read the data. Well, one of the way is the node called CSV reader. So because today we are using CSV form, the file is CSV format. So we are preferring this CSV reader. So okay, so now I will demonstrate how to use this node. Just a moment. So now I need to import my data. So today we will be using the soybean leaf disease data. Okay, so I have shared in the Google link just now in the WhatsApp group and chat box. You can see we are using soybean disease reflectance data here. So I click here, and before we run the node, right? This is the data we are using today, spectroscopy data. Okay, so so later on I will introduce further on here. Now we try to import certain or any CSV here, just to assuming that, and then as we can see here, CSV reader, so we can see the row and also the column here, and then after that we need to click apply and click OK. So after that we can see the light has been turned red to the yellow. So that means before the executions, it is in red. I try again. Yeah, you can see it is in red, and then the mark here. And after we have importing the data, and then it will change to the yellow. Okay, so I didn't click before I click apply, it still have the red and also exclamations mark. After I click apply, it will change or it will turn to the yellow. And then it is not the finish yet, because yellow is ready to go. Red is not, is inactive. So after that, after this one, because we have see the configurations and do some setting. We have do some setting and then click apply, and the yellow light is appear. So after that, we need to click execute. So only the green light is appear. So that means the operation for this the node CSV, the node for this CSV reader has finished. So this operation has finished. So that means we can go to the next one, or to drag another node and to combine them, or we can see from the interface if there's a certain node indicate that to see the result. So the green one means we have finished processing or analysis. So it's just like a traffic light in the road. So okay, so this is the lesson 1, and then lesson 2. Now we have know how to simply operate the node, and then we will be going to the data cleaning and visualizations. But before that, we go to data cleaning first. Okay, I need to re-import. Okay, actually I have shared in the Google link. So this workflow you can just import from KNIME, which is the basic KNIME section, this one. So after you have download this one, right, you just go to file and then import the KNIME workflow. So the link that I have given just been given you just now, it consists of the workflow of this this workflow. So you can just import from there. Yeah. And now we will go to data cleaning. Okay, so before we run any core analysis, for example machine learning analysis, the first part, the beginning part, we need to do some data cleaning. This data cleaning is consists of a general or basic data cleaning. It is not going into the feature engineering in artificial intelligence yet, but just a simple data cleaning. For example, if we get the data, for example, in the CSV form, it will consist some of the noise. There's the simple noise that Excel cannot do. So that Excel cannot be performed. If we want to do it manually in the Excel sheet, it is quite tedious. So in this sense, we can use some of the tools or software to help us, or even Python programming to help us to sort out this one, means this problem, so, or this difficulty. Then after that, we can proceed to the second stage. So for example, now I would like to go on the row filtering first. For example, if I want to filter the row. Okay, so if I want to filter the row, I need to provide the column. So which target I need to filter. So for this one is class, because let me introduce the nature of this data first. Today we will be using the data related to the spectral reflectance analysis on the soybean disease and do some predictions on soybean disease using the spectral reflectance that acquired from the field spectroscopy. So this data has been acquired from field spectroscopy here by taking many samples. We call it by taking many samples. So as we can see, these are the sample, and then from the 450 and 50 nanometer wavelength to the 1006 here. So this is the spectral region spectrum, and we can see from each of the sample. For example, observations number 8. So it is classified as class 0. So class 0 is healthy. So class 1 is the soybean has been detected and affected with 1% of this leaf spot disease, and then class 2 is the 1 to 3% has been affected by the leaf spot disease. Class 3 is the 3 to 6%. Class 4 is the 6 to 20%. So the analysis, I mean the researcher will go to the field and then take several samples for that particular I mean classes, severity class, so ranging from the class 0 to class 4 using these tools spectroscopy. So this instrument is the ASD field spec and handheld to in this experiment. Is the researcher also use this equipment to take it, okay, so that we can see for class 0 they have 100 samples, because of course we cannot we cannot take only one sample. It will be a bias, right? So when we want to process, so it is not irrelevant. And for class 1 it has 100 sample and so on. So okay, so now if let's say we want to do some row filtering, we can just go to class. And then we can use pattern matching. Just put 1, and then means 1 is mean we want to just to extract any relevant informations across the wavelength that related to only class 1. Okay, after that we click apply, and I execute that. After I execute that, we want to see the result. So you just take you just click here, filter. So from the row 99 until the row 199, it is regarded as class 1. So if you want to save it, you can save it. You can just drag and drop the CSV writer and then combine it from the inner node to the outer node of the row filter, and then the outer row of the node, outer port of the row filter, and connect to the inner port of the CSV writer. So the term of the port is it has the inner ports and outer port. So inner port of that particular node, that's called the input, and then the output of the of that particular node is called the output node. So later on we combine the output node of the previous node and to the current and connect them into the current input port of the current node. So you can save, I mean, anywhere, and then later on, so this filtering result, you can save it later. So this is the data cleaning. So now, just now I'm using pattern matching. We can also use the range checking. For example, in this class we have how many class? 0, 1, 2, 3, 4, right? 0, 1, 2, 3, 4. So the range checking, we can minimize and filter out in certain range. For example, if the maximum I want, for example, I want to look or filter the classes from only 2 to 3, right? So lower bounds mean the minimum. So the minimum is the 2, and then the maximum upper bounds is referred to the maximum. So it is 3. So after that, I click apply and click OK. So I execute it. 2. So it will only filter, or it will only derive or extract from the classes 2 to class number 3. Okay, basically this is the row filter. So now we go to the column filter. The procedure is the same. I need to import the CSV file. After that, column filter, it has 3 types of selections. It consists of 3 types of selections, which are menu selections, wildcard, reject selections, and type selections. For the menu selections, we can just, I mean, exclude and include any informations manually. So for example, if you didn't want to include this wavelength number 454, we just put it out. Or if we want to use it, and then we just, I mean, include, and then click enforce inclusions. So it is quite straightforward. And for this one, okay, patterns, we need to give some of the hint or tips or symbols. So for example, if I want to extract any information related to 1, and then it will be extracting and then include this out, right? For the tab selections, if we tab selection is, it will select based on the certain criteria, whether it is string, numbers, integers, several Boolean value, and so on. So for example, integer is class, because class 0 to 4 is the integer, it's not the decimal. If we include the number double, it has include the integer, and that means the decimal. As the wavelength, the mean for the spectrum is the in the form of the decimal. So if, let's say, we didn't use the spectroscopy data, for example here, if you use the date, for example from 2005 to 2022 now, and we we can use this date and the time. Okay, basically we are now know on the how to do the data cleaning, and then now we can proceed to the data visualizations. Okay, so in these sections, data visualizations, I will show only several examples. Of course, it has a you can exploit later on. Okay, so so now we will be using Data Explorer. The Data Explorer is we will be trying to use or visualize some of the basic informations or statistical information like the in the form of the histogram. Yeah. So before I go, every time a good habit, we need to go to the configure first, and then to do some settings. This is applicable for each of the operations in the node. So
Yao,
yeah.
yeah, before you proceed further, maybe it's good to check whether the students have got this installed or not. Otherwise, I think it's very difficult for them to understand what's going on.
Okay. Okay. So I think you Miss, you have installed the NAM, right? And then have you tried now?
Yes,
Some of-
sir.
Okay.
Yao,
Yeah.
yeah. Before you proceed further, probably it is good if they can see very roughly the example that people have used it for the concrete strength prediction in NIME. Before they go further, because this one is good. Okay, this one is good. They will do it further. Maybe just to give them some relevance, okay, to their course. You can show them maybe using the slide how people have used NIME for the concrete strength prediction.
Okay, doctor. Okay. Okay, so I now I roughly do some demo and show on for example, we want to predict the concrete strengths of the certain constructions materials. So this is one of the example of the workflow. And then as you can see here, we have cement. Cement is also one of the constructions materials that is necessary in the when it's want to dry one of the civil engineering work or construction work, and slag and other ingredient or other content of the in the concrete materials, and also the age. And this CSMPA is the strength. So this is our target. We want to predict this by giving all of the giving some of the inputs such as the cement strength, the age, and so on. So
Right. Go back to the table.
Okay.
Okay. This is very interesting. Okay, because what is going on here? Maybe you can. Yeah, that's good. Right. So in this work here, all right. How can I explain to them that this guy or this researcher is using previously recorded data. Okay, he got this data measured in the lab. This is not using the field spectrometer, okay, but he's using other instrumentation mechanism, okay, to obtain all this information, right? For example, all these parameters, right? All these parameters are being used in determining the concrete strength. I think you guys are more familiar with this. Have you done this before in the lab? Maybe have you done any experimentation on how to determine the strength of materials and the parameters that you use in order to come out with the final determination of the strength? Okay, is this something familiar to you? Can you comment?
No, I think no.
Okay, how you determine the strength of any materials, or this in this case here, concrete is the most important thing. Yuha, where is the slide to give some information? Is it a concrete compressive strength? Is this it? Is it concrete compressive strength? Is it correct? Is that the output?
Yeah, the output is the concrete strength in the CSMPA.
Okay. So you haven't done anything like this before in your lab, maybe in your concrete lab or something? Like say, for example, you have information regarding water, cost aggregate, age, and so on. And finally, using certain models, okay, you can estimate the concrete strength.
Concrete compressing. Doctor, I will correct that. It is we want to predict the concrete compressive strength.
Yeah, okay, fine. So maybe the students, because these people are, they are the final year students of civil engineering, probably they have done this sort of experimentation before in their concrete lab. So Haris, you have never done something like this, isn't it? You have never done something like this before.
To know the strength of the concrete.
Mm-hmm. Have you done something like this? Let's say, for example,
I'm not quite remember.
I think
Doctor, we have done the
we have tried
experiment.
this, but we didn't. Oh, okay. We didn't estimate the strength because we just we test it with the machine, right?
Mm-hmm. Oh, okay.
We didn't estimate
Yes.
with this kind of software.
Yeah. Not specifically this software. So maybe previously you have used other software, not specifically NIME I'm talking about, but maybe you have used other software. By having all the information like this, then you can estimate or you can predict, okay, the compressive strength of the concrete, right? Okay, so anyway, maybe you can check back from what you have done in the lab before, probably not this year, maybe during your previous years. Okay, so probably you have done something like this. Okay, this case study was taken from, I'm not sure where it comes from. Is it from China, from US? How? We have taken this from an example given by NIME in their website, in which they have used. This is coming from a civil engineering, probably a research or probably an undergraduate level, I'm not sure. Okay, but this is quite relevant to you guys. Okay, so we can see that in this particular case here, this researcher can predict concrete compressive strength based on the parameters given. Right? So in this case here, he used NIME as a software to do this prediction. Of course, you can use other things as well. Even maybe probably you can use Excel if you know how to do it. But KNIME is actually easier to be used because they have a lot of tools, a lot of modules inside KNIME that can perform the analysis quicker than Excel. Okay, so okay, you how proceed.
Okay, so for example, in the lab, we collected the sample of each of the input variables because we need, that's called the parameters. So cement, slash, and other parameters, and also the age, and then this is called, we call it as the in the form of the quantitative because it is in numerical, and then these parameters is called the input because when we want to run one machine learning analysis, we need to give the input, right? So this is the one you measure each and take the sample for each of the parameters that you want to measure or you that need to predict the concrete compressive strength. So this is called input, okay, the parameter, and then the last one CSMPA. For each of the sample you taken, you need to measure the strength. So this is called the output variable. So every samples we need to measure several parameters that will be regarded as the inputs in our machine learning analysis later, and then together with the output variables, there's the one we want to predict, right? So two informations is the necessary with to train our machine learning algorithm or to do any artificial intelligence analytics. So the first one is the input informations. There's consists of the quite several number of the parameters, and also the output, the target, is the target that we want to predict. So after that we do some normalizations, or the normalizations meaning in this the workflow to predict the concrete compressive strength. After that, we need to do some feature engineering. So in the feature engineering, it consists of the normalizations, minimum to maximum. If we want our data to stress from the 0 to scale from the 0 to 1, is also the under normalizations, min max normalizations. But it's of course in the statistical analysis, there are many ways to do the feature engineering. So now we are using 0 to 1. That means stress all of the parameter from 0 to 1, and also stress the output variables from 0 to 1. So it's easy for the machine to learn. So to do some, so this is called normalizations. This is the, and also called the pre-processing step. And after that, we need to divide our data into 80% of training and 20% of testing. So 80% of the training, this means the 80% of this portion here, the portion here, how many row? Okay, you can calculate later you can, out of this at 1029 row, 80% of this will be randomly selected to train the model. And then of course in the other way around, 20% of this row in the data, raw in the data, will be taking out and then uses for the testing. This testing is to do the predictions. So later on, from what the algorithm has been trained, it need to test and it need to do the prediction on the testing data. That's the 20% of the overall whole data. And then after that, there are many algorithms, machine learning algorithms. So to train the model, this is